Hi, this is Sue McBride, and in this PowerPoint, we'll be discussing a few cautions about graphics from Section 3.4 in Statistical Reasoning for Everyday Life. And this is one of the true lessons where this is something you want to take away from just this class and apply it to any time you see graphics out there in the media, like we talked about in the last PowerPoint, or at work, wherever. They can be very misleading due to perceptions. All right, so let's take a look at how you get some distorted perceptions or perceptual distortions, which may be intentional or unintentional, but you just have to be very aware. So this example of a dollar bill I've seen in quite a few places. So before you read all the stuff, just take a look at the dollar bills. So we have the dollar bill in 1980, and then in 1990, and then in 2006. And you can see the ideas they're saying it's shrinking. But if you took the actual dollar bill over there in 206 and laid it on top of the one in 1980, it's less than a fourth of what the size is, and that's where your brain goes. All right, so the lengths of the bills actually are supposed to represent the data, how long it is, but our eyes tend to focus on the area because it's a two-dimensional object. That dollar bill is a length times a width. So for example, the right, I should say bill, is supposed to show that a dollar in 2006 is worth 41% as much as the dollar in 1980. Well, if you measured its length, that really is a little less than half, but when you compare it to the whole dollar bill, it's about 17% or closer to an eighth. That's crazy. So your brain, your eyes tended to focus on the area instead of the length, which is what they meant. So even though the lengths of the dollars are proportional to their spending power, our eyes are drawn to the areas, which decline more than lengths. Or in other words, the area is a lot smaller than the length is, proportionally speaking. Now look at this one. Oh my goodness. Again, don't read the words, just look at the pictures. This TV from 1980, homes with cable TV, looks so much bigger than that one. The 2005 one looks tremendously bigger than the 1981. This time they didn't go with just a length to an area. Here we've got a volume, which is actually length times width times height. So you can end up with quite a huge proportionally incorrect idea. All right, so now back to what it says. So the number of houses with cable TV increased by a factor of about 4 between 1980 and 2005, as shown by the heights. And I couldn't even figure this out when I first looked at this. I'm like, what's times 4? So it's the height that they're looking at. So if you scooted it over and you stacked up, you'd get 4 of those 1980 TVs at the same height as the 2005. But again, we're looking at the volume, the length times width times height, which factors, remember, if you've got 4 cubed is 64, it makes it look 16 times bigger than it really was. So the heights of the TVs are what's important. That's the what the point is, but our eyes are drawn to the volume simply because it's a three-dimensional figure. All right, now here we've just got our regular graphs. If you look at these two, they don't look anything alike, but they're actually graphs of the same thing, women as a percentage of all college students. If you look at the left hand, it looks like it fluctuates all over the place. If you look at the right hand, it fluctuates a little bit, but not as unsteady as it looks in the left-hand side. The reason? Both graphs have the same data. So if you look, you see the ordered pair 0, 40. You see the ordered pair 19, 20, up to 45, halfway between 45 and 50. So the points are the same, but what's different is notice that you didn't start at 0 on your vertical scale of percent women. You started at 30. So you've left out the 0, 10, 20 that's represented on the right-hand side. So when your scale starts at 0, it looks much different depending on how high up you went. Also notice on the right it goes up to 100. So my scale on the left is 30 to 60. They just kind of encompass the highs and the lows. But if I go from 0 to 100, which is the full range of percentage, it goes from 0 to 100, then you get a much different look. So both graphs show the same data, but they look very different because their vertical scales have different ranges. So 3.42a is the one where I'm going up exponentially, and yes, I could make a prediction fairly easily, but for the one on the right, B, not really, because it just looks like a vertical line. It's very hard to read the differences from one year to the next. So that's another good reason for the exponential. It more clearly allows you to see changes from one value to the next. Oops. There we go. We're going to do one like this where we do some actual numbers, and there's one on your homework. It really helps to hit the help me solve this to talk you through it. It's a little more clear than I can do on this PowerPoint. I'll just stop with that. All right, so we're going to do one from the homework in the book shortly to take another look at this. But again, you have to very carefully understand what percentage change is comparing it to the prior year. So if it increased from the prior year, the graph goes up, but if it decreased from the prior year, it goes down, but that doesn't mean it's still not increasing in actual costs overall. Oops, linear, which it's not necessarily either, because again, the scale along the bottom changes. Now notice 2013 has 7 billion, so what they're doing is predicting that it will be up to 8 billion in the year 2028. So we'll have to see if that happens. All right, but the idea of the pictograph is those people are just a little misleading. We don't need them, and it makes it look like it's linear, but it's not. What's going up by ones is the number of billion, not the years in which it happened. All right, let's take a look at some ones from the homework. And again, on my math lab, you're going to be wanting to click on the icon that opens up the picture or enlarges it as needed. All right, so these first two are just kind of questions about vertical scale. So envision a line chart that has a vertical scale with 0, 1, 10, 100, 1,000, 10,000. What's the name of such a scale? All right, we went over that a minute ago. That's the exponential. And the advantage of that is when your vertical values have such a big range that you simply can't fit all the numbers in there. That's when it's nice to have an exponential scale. All right, sugar cubes. To show how sugar production doubled from 1990 to now, an illustrator draws two sugar cubes. So remember, a cube is length times width times height. So the first cube is drawn with a length of 1 centimeter. So if you envision that, that would be 1 times 1 times 1. Its volume is just going to be 1 centimeter cubed. But the second cube is drawn with a length of 2 centimeters on each side. This is like the TV one. So the volume of that one will be 2 times 2 times 2, which is 8. So the volume is 8 times, even though really it only doubled if he was trying to show the length of 1 to 2 centimeters. But because a sugar cube is a cube, he went with that shape. So it's really twice as big, but it would look like it was 8 times as big if you did the volumes. Number 5, let's talk about car mileage. This one shows the highway fuel consumption in miles per gallon for the Chevrolet Aveo and the Honda Civic. So how is that graph misleading? How could it be drawn so that it's not misleading? All right, so whenever I see a graph like this, I automatically go look at what things are being measured. So we can tell from the bottom it's car mileage, and those are the two cars. But what's on the vertical is highway fuel consumption. And then I look at the scales. Well, there's no scales across the horizontal, but up the vertical, darn, we're starting at 30. So when you only go from 30 to 40, the Honda Civic looks like it has a bigger change from a little below 35 to a little above 35. But if you start at 0, if I redraw that to start with 0 and go up to 40, that what looks like a 2-point difference is negligible. They look almost identical. So starting that at 0 would make that less misleading. Number 11, this is the one I was talking about with the percentage change. Here, this graph is the percentage change in CPI. Remember that's your consumer price index we talked about back in chapter 2 over recent years. In what years of those displayed, so they've displayed from 1990 up to 2010, was the change in the CPI the greatest? So I want the biggest change, and remember each bar represents change, so I'm just going to go pull out 1990. That's my biggest change. What happened in 2009, here it went down into the red, so that means my percentage change actually was in the negative, which means it decreased. So the prices in 2009 were lower than those in the prior year of 2008. So my percent change went down. My cost was less. So how do actual prices in 2010 compare to those in 1990? So if I go over to 1990, it looks like my percent change from the previous year was about 5.5%. And if I look at 2010, from the previous year, it's a positive about 1.8 plus that negative 2. So if I add those two together, my price has increased about 0.2 plus 1.8, so about 2%. So from the year before. Okay, based on this graph, what can you conclude about changes in prices during the period shown? Well, it shows that we had in 1990, the percent change was still up, but it leveled off a little bit, and it was a little bit lower from 1992. It was still going up, but it was going up in smaller increments. And then back in 2009, it tanked, and then it started to go back up again. And remember, this is the percent change is positive, means the prices were going up by as much as this as a percent of the year before. Okay, so go ahead and do your homework. That finishes up chapter 3. So once you finish 3.4, you'll want to study for your chapter 3 quiz. And after the chapter 3 quiz, your first test will cover chapters 1, 2, and 3. So hopefully you've made your appointment at this point at the testing center or with ProctorU and find that information on Blackboard. Okay, email me with questions. Thanks. Bye-bye.